All right, let's dive right in. We're going to tackle one of the biggest, most fundamental puzzles in the entire universe. It's a question that involves every single living thing, from a tiny bacterium all the way up to, well, you. And the question is, how is life even possible?
So here's the paradox. On one side, you've got the unbreakable rule of the universe. Things fall apart. Energy spreads out, buildings crumble, and everything just naturally moves from a state of order toward chaos. But then you look at life, and life does the complete opposite. It takes simple, messy molecules and builds them into these incredibly complex, highly ordered things like cells and organs and, us.
So what gives? How can life get away with this? How can it swim so powerfully against this constant cosmic current pushing towards chaos? That's the big mystery we're going to solve today.
To get to the bottom of this, we first need to understand the rulebook. We have to unpack the fundamental laws of energy, a field of science you've probably heard of called thermodynamics.
Okay, rule number 1 is actually pretty straightforward. You can't just create energy out of nothing, and you can't make it vanish. It's always there. You can only change its form, like a plant turning sunlight into chemical energy, or you turning the energy in your lunch into the energy you need to walk around. The total amount of energy in the universe, it's fixed.
Now, the second rule, this is where things get really interesting. It says that for any process that just happens on its own, the total amount of messiness or disorder in the universe always goes up. Think about it. Your clean room doesn't just magically get cleaner, right? Over time, it gets messier. That's the second law in action. It's this powerful one-way street toward chaos.
Now, this built-in tendency for things to get messier has a proper scientific name, and it's one of the most important ideas in all of science. And that name is entropy. We use the letter S to represent it. Really, all it is a way to measure disorder. So, a perfectly ordered ice crystal has very low entropy. A cloud of steam with molecules bouncing all over the place. That has super high entropy. And the second law tells us that the total entropy of the universe is always increasing. And we see this in chemistry all the time. When your body breaks down one complex food molecule into lots of simpler molecules, like CO2 and water, you're going from one ordered thing to many disordered things. That's a huge increase in entropy. But on the flip side, if you take separate hydrogen and oxygen atoms and form a single ordered water molecule, you're actually decreasing entropy.
Okay, so this leads to a really crucial question. If some reactions make things messier and some make them neater, how do we know which ones will just go? Happen spontaneously without us having to force them? Is it all just about entropy?
Well, it turns out entropy is a huge piece of the puzzle, but it's not the whole story. To really predict what a reaction is going to do, we need something even more powerful. We need the master key that unlocks this whole thing.
This is where a brilliant scientist named Josiah Willard Gibbs comes in. He came up with an incredible equation that combines two different things: the change in a system's heat, which we call enthalpy, or delta H, and the change in its disorder, our old friend entropy, delta S. And when you put them together, you get this one incredibly powerful value, Gibbs Free Energy, or delta G.
And here's the best part. You can forget all the complicated math for a second. All you need to do is look at the sign of delta G. If it's negative, the reaction is called exergonic, and it means it can happen all by itself. It's favorable. If delta G is positive, the reaction is endergonic, and it just won't happen, not without a serious input of energy.
Let's take a super simple example, boiling water. We all know that at room temperature, a pot of water doesn't just start boiling on its own. That's because its delta G is positive. But look at this graph. As you crank up the heat, that entropy factor gets bigger and bigger, until finally, at 100 degrees Celsius, it overtakes the heat factor. Delta G flips to negative, and bam, boiling becomes spontaneous.
So, let's bring this all back to life. The reactions that build things like proteins and DNA, well, they create a ton of order, which means they are highly endergonic. They have a positive delta G. So how on earth do our cells pull it off?
This is where life pulls out its secret weapon, a little molecule called adenosine triphosphate, or ATP. The easiest way to think about ATP is like a tiny rechargeable battery that every single one of your cells uses. When a cell needs to get something done, it just breaks a bond in ATP, and that reaction is super exergonic. It has a very negative delta G, which releases a perfect little packet of energy.
And this point is absolutely crucial. The very act of building and maintaining a living thing is fundamentally non-spontaneous. It's endergonic. It requires energy constantly. Creating order in a chaotic universe is expensive.
So here is life's most elegant, most brilliant trick. It's called reaction coupling. The cell takes a reaction it needs to happen, but can't on its own because its delta G is positive, and it pairs it or couples it with a reaction that is super favorable, like breaking down ATP. That big negative delta G from the ATP breakdown basically pays for the positive delta G of the building reaction. You add them together, and the whole process becomes favorable. It's genius.
Okay, let's put all the pieces together. We can finally solve that paradox we started with. How does life create all this amazing order in a universe that is hardwired for chaos? And the answer is just beautiful. Life doesn't break the rules. It doesn't cheat the system. It doesn't violate the second law of thermodynamics in any way. In fact, it has become an absolute master at exploiting that law.
Here's the grand bargain. In order to create these incredible, beautiful little pockets of order that we call life, an organism has to pay a kind of disorder tax to the universe. For every little bit of order it creates inside itself, it has to release energy, mostly as heat, out into its environment. And that heat makes the molecules in the air and water around it move more randomly, creating way more disorder outside than the order it created inside. So the total entropy of the universe still goes up, just as the law demands.
Which leaves us with a pretty profound final thought, doesn't it? Our existence isn't some rebellion against the laws of physics. It's a direct result of them. We are just these temporary, incredibly complex patterns of order, powered by a constant flow of energy, that have figured out how to win a cosmic gamble against chaos, but only by paying our energy tax back to the universe. Thanks for joining me on this explainer.